Good morning, good afternoon, and good evening to all of you. Bonjour and greetings from France. I am Jean-Pascal from Cryo Bio System. It is a pleasure to welcome you to our second 2021 webinar. It is great to have you all online today. First, before starting, I would like to give you some information regarding the way to ask in writing your question to David Mortimer. Okay, if you want, and we will be very happy if you do. If you want to write your question in writing, you just have to open the control panel on the top right side of the screen, like it's showing here on the schema, okay, by clicking on the red arrow. Then you just have to write your question and you just have to send it. Prior to writing your question, please do not forget to mention the country where you are writing from. I will say that very shortly in French for our French speaker people. Bonjour à tous, je suis ravi de vous retrouver pour notre webinaire. En cas où vous vouliez poser des questions, vous êtes bien entendu les bienvenus. Cliquez uniquement sur la petite flèche qui se situe dans le carré rouge ici sur la slide. Écrivez votre question et ensuite vous pouvez nous l'envoyer et on se fera un plaisir de pouvoir bien entendu la traduire pour le docteur Mortimer. I am pleased to welcome and introduce Dr. Mortimer. I know that David is already very well known among the IVF and the biobanking community. Many of you have already met him during a symposia or convention he is attending. David is based in Vancouver, Canada, and he is actually the president of Ozoa Biomedical Company. He is also a member of the Canadian Standard Association and Standard Council of Canada. His main interests and area of expertise are just, to name a few, human sperm phytopathology, such as motility and morphology, diagnostics, andrology, ART, laboratory technology. He has participated to numerous publications and presentations with more than 160 papers, book chapters, and books. And he has participated to more than 300 conference presentations, postgraduate courses, workshops, and symposia worldwide. Now it's time for David to share his knowledge and secrets with you. David, the floor is yours.
Merci, Jean. I'm waiting for the link to share my screen. Can you see my screen? Jean, can you see my screen?
Yes, David, it's okay.
Merci. Well, hello, everybody. It's still a very dark Vancouver here at just after 5:30 in the morning. The disadvantage of living so far west is that to communicate with the rest of the world, we have to start very early in the morning. So thank you, Jean, for the introduction, and I'm very happy to be have been invited to give this second 2021 webinar for Cryo Bio System. The topic I was asked to speak on is Optimizing Cryotank Organization, and let's just get straight into it. Just got to put the get my pointer, and we will move on. So Jean asked me to give a short history of how much I've been involved with sperm cryobanking. It's been a long time. I first took over responsibility for the sperm bank, which was both donors and patients, in Edinburgh in 1977, literally just after I got my PhD. We were using half-mil IMV straws in those days, and we used to code the straws with these lines as per the CCOS system. I actually went and spent a year with Professor Georges David and his team in Kremlin-Bicêtre, working on sperm motility rather than sperm cryobanking, but I was there at the headquarters of CCOS. So basically, I've frozen human sperm in straws exclusively for more than 40 years. Throughout most of the 80s, I ran the sperm bank, which again was both donors and patients in Calgary. Again, we were based on 0.5 ml IMV straws in those days. And in the late 1980s, this was actually the biggest donor sperm bank in Canada. I moved to Australia in '91. Along the way, I also became an advisor to Cryos in the mid-90s, and they were at that time they started using the high security straws. We've frozen embryos in straws since 1989, and we've been doing embryo oocyte vitrification in the HSV devices since 2013. Why use straws? This was explained to me very early on in my career, and it's very clear because of their smaller radius. And because of this, straws are much better than cryotubes in terms of heat transfer, and hence they achieve better cooling and especially warming rates. In terms of cooling here, you can see it's freezing a sperm at -8 degrees C per minute. You can see that the desired cooling curve down here is much slower with the cryotubes. Much worse, though, is when you're thawing, and even if you're thawing at 37 degrees, the thawing time is actually much, much slower in the cryotubes compared to any type of straws. And the importance of this will come up later in the webinar. But just remember that the straws, they thaw very, very quickly, which perhaps makes them a little more risky in terms of how you have to handle them. But in terms of cryobiology, it is far better for specimen survival and the competence of the specimen post-thaw. So cryobanks come in all shapes and sizes, small ART ones like this, ones that are getting a bit bigger, ones that have got quite large. Then you can go into the high capacity tanks of various types. This is actually a friend, the California Cryobank. And some of these tanks become enormous, and the whole question about inventory and how you control things, how you find things, is obviously much more difficult when it's this large compared to smaller tanks. But the same systems can actually be used regardless of the size of the cryobank. So our preference, literally since 4 decades ago, has been to standardize using the 65mm diameter goblets and the visotubes inside them. Some people call these things mini goblets, but I'm using the appropriate word as per the CBS, the manufacturers, and call them visotubes. The color and shape options of the visotubes in particular, as well as the colors of the goblets, make storage units easy to locate even in the fog that you see in the top of a cryotank. Obviously, the devices are always labeled, and the actual storage units, the visotubes, are labeled with marker pens or whatever as well. But trying to find something in that fog is much quicker by shape and color than is by trying to read labels. And you can organize these goblets into canisters. You can use the short tanks if you're using like a ready-use tank, which will have just 1 layer of goblets, or the standard 11-inch canisters, which will do 2 layers, or in larger carriers for up to 5 layers in these very high capacity tanks. And this makes them for very easy handling of your material. If you're using these goblets, then you've got interchangeability of goblets between canister or carriers of these multi-layer devices. And of course, you can easily move a canister or a carrier between cryotanks very easily. And that will come up in the how to manage tanks later on. Visotubes, I find them much easier to work with than with canes and cryo cassettes. And it also allows us to have many more locations, storage locations per canister, than you would have with cryotubes on canes or with the use of cryo cassettes. Why did I choose CBS high security devices? Well, we wanted to continue using straws for freezing sperm to get the optimum cryobiology, so we need to stay with small diameter specimens. If you have larger specimens, you can use the tissue straws, which are still straw shaped but just a bit fatter, or you can use HS tubes if you really need to for the larger specimens. All high security devices achieve effective biocontainment. They're virus proof in both directions. It means there is no risk of cross contamination within the cryotanks. In fact, under the EU Tissues and Cells Directive, high security devices constitute independent storage. There is no need for quarantine tanks if you're using these sorts of devices, which was a very big, complicated issue if you're going to try and use cryotanks properly. I'll discuss that in question time if somebody wants more information on that. So the HSV is the only vitrification device that's validated with effective biocontainment, And all of these HSV devices are not fragile even at -196. We all remember the old straws and how easy it was to break them, especially the embryo straws, when they were frozen at -196. They were quite fragile. I have some slides at the end of the talk about the history of the high security devices and their validation in terms of biocontainment. I parked it at the end because it's not key to this lecture, but the information is quite difficult to find. So we'll come to that just at the end of the talk. And of course, with these devices, we've got numerous options for easy identification via device color and secure labeling techniques. So we've got straws. These are sperm or embryo straws with the plug in the middle to give the secure second compartment, which is not for specimen storage, but for storing an ID rod, which allows the identification to be sealed inside the straw. The sperm straws have got the traditional PVA powder plug with the 2 bits of cotton wadding, and with the upper wadding is actually color coded in those versions. Tissue straws, I say, they're just a bit fatter. HSV devices, the tubes, all of these need to be sealed with a sealer. The current version of the Model 3. That's because you need to get the temperature and pressure and timing exactly right to guarantee the weld that appears on the end of these straws. That actually is what gives the guaranteed seal. So the options for identification of these devices, with the 0.5 ml sperm straws, we've got the colored plugs, as I said, and we can use external labels. We can also use external colored sleeves on the straws that are trapped by the flattened tab on the end after it's been sealed, so they can't be lost either. And you can put labels on those as well. So we've got 2 or even 3 layers of identification possible on these straws that can't come off. These 0.3 ml volume straws, they're the same size straws, but they just have that second compartment, and you've got colored rods that go internally, and you can also use external sleeves with labels. The HSV devices come in 6 color options, and they are compatible with the adhesive cryo labels from people like Brady. And the HS tubes have colored inserts, again 6 choices of colors, and you can use external cryo labels, of course. So we've got a number of ways of identifying these things that, if used in conjunction with identifying the location, give you a very quick way of knowing you've got the right specimen. At least you've got to the right specimen, and then you can do the final check of the actual label itself, whether it's written in text or it's a barcode or whatever. So cryotanks come in all shapes and sizes. Most people will be familiar with 1 or 2 of these regular size tanks, shall we say, the 35 or 47 liter tanks. But you can see these larger tanks. This is the Taylor Wharton K series, a 10 model, and these actually will hold in not much more than the floor space of an HC35 the contents of at least 5 HC35s. So it's much more space efficient. And these larger ones, in this case it's a Thermo-Cryo Plus 3, they'll hold at least the same as 10 of these smaller tanks, admittedly in a larger footprint, but still nothing like proportional. So it gives you a much greater capacity within your bank. And people say, well, how on earth do we find specimens in these big tanks? And that's what I'm going to show you. So many of you will be familiar with the canisters, obviously, and the use of canes inside these canisters with the visotube containing some straws. In the old days, the embryo straw for embryo storage used to use just 1 layer of storage because the upper part was half a visotube turned upside down with holes poked in the top of it, so the liquid nitrogen could fill it. The air would come out the holes to keep the straws from floating out. Or you could use 2 layers of straws, 2 layers of visotubes with straws, so that the bottom of the lower visotube essentially stops things floating out the bottom one, and this tab on the top of the cane stops things floating out the top one. So there's ways of obviously color coding these. You can color code the canes, and of course you can put the sheaths around them in order to stop things escaping if you're using cryotubes. CBS has this system with these large plastic canisters which don't have handles. These are designed for use in the larger capacity tanks, although there's nothing to stop you using these types of canisters in them as well. And in this case, we've got 1, 2, 3 layers deep, and you can see when you've got multiple layers, just as for getting goblets out of the canisters, you have a lifter. It's just a very simple piece of flat metal and little L shape, but it just allows you to lift them up and access the lower ones. The carrier systems I'm talking about are designed where there's a spring system that is sufficiently flexible even at liquid nitrogen temperatures to allow you to put the goblets into the the carrier, and there's a shelf here for the upper one, which acts as the lid for the lower one. There's a top, again, that stops the risk of floating out. In high capacity tanks, you can have lots and lots of these plastic canisters, or what do you want to call them, in here, and you can see that there are in fact 2 or 3 layers of goblets inside here, and you can see the lifters for lifting them out. So you can use these lifters, can have plastic flags to give you different colors, so you can go and find which one's much more easy than trying to count number positions, for example. And those flags, you can put numbers on them so you can easily find the yellow, yellow 17 or something. Again, using, and that's that flag is on top of the lifter to lift the goblets out of the canister. The important thing to remember is that even though these goblets might have holes in them, the visotubes only have a hole in the top, which means when you lift them out, they stay full of liquid nitrogen, which means you're protecting your specimen. And we're going to consider that more as well. So within this whole scheme, this ecosphere of storage, if you like, there are many options in terms of different shapes and sizes of these visotubes, as well as the colors. The different shapes and sizes would allow you to store of different capacities. And of course, this is important if you're storing donor sperm ejaculates, where you may have 10 or 15 straws per sample, or you're storing blastocysts for a patient where you might have 2 or 3. And you don't want to use a location that will store 36 straws if you're only going to have a small number of straws from that one sample. So you can scale for capacity. So break down the capacity of the goblets by dividers and lots of visotubes of the same color, or with perhaps one of a different color and some rods so you can identify them easily. I've never used this particular system. We've always preferred this system where we have different shapes and colors of visotubes. In this case, this is designed for sperm storage, where we have relatively high capacity of these things. And going back to this, it was the traditional half-mil straw in these large round or polygonal tubes, and the polygonals would hold 15 straws and the large round ones would hold 8 or 10, so we could scale them to match the size of the ejaculate samples we were storing and waste as little space as possible. More recently, we've looked at more high capacity methods, in this case using the large hexagonal visotubes, but by subdividing them with smaller colored visotubes, so you've got different layers of color selection to get to the one location you want, where you will only have perhaps in these very small visotubes 1 high security straw or 3 HSV devices. So right down to the individual patient very quickly. Daisy goblets are one of the most common approaches, and this is a traditional daisy goblet, 11 colors around the outside and the center one. Each of these is very high capacity, and we've subdivided these for a long time now by putting a visotube inside to make this into 2 compartments. And we can identify these by giving them numbers, outer and middle, and this white central one is identified separately. So we can get either 11 locations by color plus the center one, or we can actually make it up to 23. So as I said, even though these goblets may have holes in their bottoms, and the lids have holes as well, the visotubes don't have any hole apart from one in the top, and so they remain full of liquid nitrogen. I mean, samples stay stored at -196, even while you're handling this. You can even take this out of a tank and put it into a working box externally, and it's still full of liquid nitrogen. So this is first part of a table that we've prepared for a second edition of our book on Practical Guide to Basic Laboratory Andrology, due out later this year. And a simple way of identifying locations. First level is the cryotank, and we typically give them letters. The second one with a canister. If you've got 6 or 10 by 11-inch canisters, then you'll have a number going from 1 to 10. And so this is, for example, for canister number 4. And if you're using cryocanes with cryovials or whatever, you can have 50, perhaps up to 17 canes. So let's say this is tank E, canister 4, cryocane 15. If you put visotubes on those cryocanes, give you 2 layers of straws, then you can be upper or lower. This is lower. If you're using cryo cassettes, it's similar to the cryocanes with cryovials, and you would have a number of cryo cassettes. These are often used in the larger diameter canisters in some of the other brands of tanks. And of course, with daisy goblets, we've got 2 goblets per 11-inch canister. We call those upper or lower. So E04, tank E, canister 4, upper goblet. And we would often have distinct colors for each layer as well, but the colors, you could use colors or upper, lower. And so within these, we can identify them then by color. So this one that's got a star on it is actually the black one. The numbers, we have to be a little bit inventive sometimes. So instead of G for gray, because G is already taken for green, we call it D for dove gray. And the pistachio color that the French seem to love, we usually call it mint, because P has already been taken for pink. So in this case, we've got E04. Now it's K for the black one. And if we've used the second subdivided here, we can have KO or KM. With the CBS goblets, where we use the different shapes and sizes of visotubes, we can have the canister just the same and goblet the same way, but then we can use hexagonal, polygonal, round as single letter as the first letter, and then the color as the second one. So this one here is the now we're saying we're in the lower goblet, and we've got a polygonal violet one, not to be confused with the polygonal round one that may be next to it. So we've already got 2 very many layers easily identified. And of course, with this hexagonal system, we can make it using the colors as well. So here we've got the small visotubes inside, and if you could actually even put another one of them in the gaps around the outside. In fact, this is a trick. If you, instead of using the very small visotubes around the outside, if a couple of them use the slightly larger ones, they actually squeeze everything tight, and the whole system here is actually fixed inside the goblet. It won't pop out. So here, if we now use these, where we can use the EO4 lower, and then we've now got the yellow hexagonal, and we've got a red straw, a red visitube inside, we can get 49 locations. If we use the external one, in this case the external orange one, we have got 55 locations per goblet. So if you think about a standard HC35 tank, we can have 20 daisy goblets with 12 or 23 locations. This is if you've divided the wedge segments into 2, and so you've got 240 or 460 locations. With these hex goblets, we can get up to 1,100 unique locations in an HC35 tank. And as I said, this is especially useful for cases with only a few devices, storing, for example, blastocysts. With high capacity tanks, this is where, for many embryologists, their brains start to hurt, trying to imagine how they're going to manage these things. This is a Cryo+3 because it was used with one of our clients recently. And there is a system that will give you up to 66 carriers with 4 layers of goblets. So we would call this the top, upper, lower, bottom, and we use colors to tell them: red, yellow, green, blue. In this case, with 66 carriers, they're in a very minimalistic frame, and it takes a little bit of practice, but once you've got the hang of it, it's very simple to get these carriers in and out. The problem is that towards the back, they can be hard to reach if you can't get around the sides of the tank. And that means that if you want to get around the back of the tank, when you've got tanks close together, you need a thing like this cryo lift, which is a motorized lifting device that will hook on and lift them up. Problem is that with these tanks, these frames, they must be lifted exactly vertical, which is quite tricky. So an alternative system is one using these quarter segments that give us there's 13 units here, so that gives us 52 locations in one of these tanks, which gives us 208 goblets. So less than this, but much easier to work with, especially if the tanks are close together, as you can see here, and you have to use a cryolift for lifting out the rear ones. So with this, with this approach here, we've got 4 layers of goblets, up to 11,400 storage locations in a tank. All of the specimens remain full of liquid nitrogen during access, and the base for the layer above, or the very top lid of the system, will prevent any floaters. Now, when we're handling these specimens, why am I keep repeating they stay full of liquid nitrogen, they stay at -196? The important thing is there is a risk of ice recrystallization damage even while the specimens are still frozen. The glass transition temperature of water is around -132. During warming, as energy is returned to the system, frozen water molecules return to their natural orientation. Very small ice crystals have a large surface area to volume ratio, which makes them unstable, and so they tend to fuse together as things warm up, even if it's still frozen, to reduce that ratio. And as I say, this happens at temperatures above -132. So within a very few seconds for straws, you will get above -132, and this recrystallization will continue until the melting point of the cryo medium has been reached. And even if the specimen doesn't thaw, so you've warmed it up a bit and then put it back in again because it was the wrong one, or it was next to the one you wanted, for example. The thing to remember is any ice recrystallization is irreversible, therefore cumulative. So specimens that have been in and out of a bank numerous times may well have so much damage that when they are finally thawed, they are non-functional. So all this is a problem because this is a significant risk when transferring specimens into your tanks, out of your tanks, during audits especially. And when you finally come to thaw things, warming must be as quick as possible. So of course, straws have the great advantage here, but you've got to remember that there is still a period between -132 and the melting point. Why am I so concerned about ice storage? As I said, we have this safe storage area down here, and then we've got this increasing rate of ice recrystallization we get up to warmer temperatures. So the recrystallization rate is lower here than it is here. So the more time it spends in the upper part of this red zone, the worse it is. And as we get above the melting point, then we have to then start thinking about the fact that the cryoprotectant agents we're using are actually toxic. So the toxicity goes up as we get close to 37. So we want to warm them quickly, but we also want to avoid toxic damage. So this is some work that was done many years ago. Paper's almost as old as I am. And this was just some water that was coated onto a wafer and then frozen ultra rapidly, and then put into an electron microscope, and then the temperature was controlled internally. So the one I'm showing you down here is -70 for half a minute. So 30 seconds at -70. So that'd be about here for half a minute. And you're saying, well, that would never happen in the way we handle things. Well, it does. So here we just look at the relative diameters of the traditional straws, the CBS straws, and then the Nunk type cryotubes. Not necessarily Nunk, any brand of cryotubes are about the same diameter. You see they're much greater. And also they've got much thicker walls. And walls are plastic, and plastic's an insulator. So heat transfer is much worse with these cryotubes. So let's look at this thawing here at ambient temperature. So the red box here denotes the danger zone from -132 to the melting point. And you can see that straws can go through this very quickly. But obviously, if you thawed at 37, they'll go much faster. Do you remember that earlier graph showed them much more clustered to the left-hand side, very close to the y-axis. But look at what happens here, or ambient temperature for a standard cryotube. It's in this danger zone for 800 seconds before it's completely thawed. 800 seconds, that's a lot of time. Your 30 seconds is this bit down here. So you're certainly in this danger zone here for a lot more than 30 seconds. So ice recrystallization is going to get to be massive. But of course, it starts at the outside. So if you look at the radius, even at 3 millimeters of a specimen, you can see that the temperature warms up very quickly at the outside of the specimen, but much, much more slowly at the inside of the specimen. And this is 3 millimeters, and these are more like 10 millimeters. So 5 or 6 millimeters in radius with a plastic insulator on the outside. So heat transfer is poor through these. So of course, we have this risk of inadvertent warming during handling. So smaller radius specimens are more sensitive to increases in temperature, and that will lead to inadvertent warming during handling. So this is the downside of straws, but for me, it's something we can easily manage in our work practices. But we carefully train people to do this properly, of course, and that's completely counters the risk of the straws, and we can then take the advantage of the cryogenic benefits of the straws. So that, as I said earlier, the issue is when you're putting specimens into your cryotanks, when you're just looking for other specimens, if you keep lifting things out to look for them, during the audits of specimens that are in long-term storage, and of course when you finally move the specimens from the cryotanks. So proper handling of straws will mitigate these risks. And I'm going to point out here that vitrified specimens are at even greater risk because they've got even smaller mass than a straw, because most of them is not specimen, it's just air, or very, very small specimens. So vitrified specimens warm up even faster than small straws. And when you're thinking about, oh, well, we know that vapor, the nitrogen vapor can be minus 160, it will freeze the specimens again quickly. Well, here's another thing to think about. It's high school physics, but if you're trying to recool specimens, it depends on the heat of vaporization of the cryogenic material. And in this, liquid nitrogen itself is about 1,500 times more effective at cooling materials than its cold nitrogen vapor. That's why you try and do control rate freezing using nitrogen vapor, because it will cool things much, much more slowly than liquid nitrogen itself. So liquid storage is a much, much safer option for cryogenic standpoint. So to keep things safe, always keep your materials stored, immersed in liquid nitrogen, and during handling. So if you do this very often, the upper specimens here aren't even at minus 160, they're now very much at risk. So all the time you're searching for the right one here, these are all warming up and accumulating damage. So this is a big problem with these sorts of handling techniques. Even this older technique we used to use, where you would have this thing full of liquid nitrogen, pull it out very quickly, up and into the top, up and into the top. So this is liquid in here, so you still got a few seconds, and that's a risk. So we changed over then to having this immersed and working inside. Now that means these sorts of dewars are very poor ergonomics for being able to do this. So we work in transfer boxes, just standard styrofoam boxes, usually that people ship us products in, so they don't cost us anything. So here we've got a canister with a goblet, and this goblet is being put into the bottom here where it's under liquid nitrogen. You can tell it's liquid nitrogen, not water, like this one was for the photograph, because we've got the fog. But we can still see the shapes and colors of the locations inside here. So we've got one, and we've now got the other one that's from the cryobank, and we can now put them together. And we're doing it in this one because this is tall. So this is full of liquid nitrogen almost to the top. So we can move the specimens between one goblet and the other goblet, between visotubes, with them never coming out of the liquid nitrogen. Cryotank audits, the bane of everyone's lives. Nobody enjoys doing those. But some jurisdictions recommend or even require a complete verification audit of the cryobank contents against records annually. I once told a past head of the HFEA that she was probably responsible for, via the requirement for annual audits, for destroying more embryos than anybody else in the country. She wasn't amused. And she said, well, isn't that up to the embryologists to be properly trained? And I said, absolutely right. But many people are not as careful as they should be. So requiring audits is the root cause of the risk, alongside the handling techniques. So this is an arduous task, and it's a very risky undertaking, can easily lead to specimen damage or even loss in biological terms. You won't lose the specimen itself, but if there's enough recrystallization occurs, it will destroy the specimen biologically. So the question that I ask people is, if there's no evidence of discrepancy between the records and the cryobank contents, why would an audit be necessary or justified? And there isn't a real answer to that. So the approach was taken here in Canada a number of years ago with the Canadian Standards Association reproductive tissues standard, was that it's a much safer approach if a policy is created by each laboratory, bank, clinic, whatever, that says that only if more than a certain number of discrepancies, perhaps 3, on the grounds that one is happenstance, twice is coincidence, the third time do you have a real problem, if you have, say, 3 discrepancies between your records and your specimens within a certain period of time or a certain number of specimen retrievals, only then would you have justification for saying we need to do an audit. So you don't, for me, this is very dangerous practice, and I would fight tooth and nail not to have to do it. And I would ask the regulators why I have to do it if there's no evidence that in my bank we do not have an issue. And we have a policy that will establish active action if there's evidence of an issue, of a possible issue. Backup cryo storage tanks. There's been a lot about this recently, perhaps because of the recent failures in the United States. and other countries. And many regulators require you to keep an empty backup tank that's at least equal in capacity to your largest storage tank so you can transfer specimens quickly. Of course, you keep this tank about half full of nitrogen, not full, because if it's full, you can't get any specimens into it without bailing out nitrogen. And if it's warm, then of course, it's going to take you ages to prepare that tank for storage. So if you have warning, and this warning can be quite substantial. If you are looking here, what happens when with temperature storage, so storage monitoring by temperature or by liquid level. If you work with liquid level, the warning can occur right back here. So let's take that as time 0. The sensors come up, is now out of the liquid nitrogen. That's not a normal state. The alarm is going to go off. And you now have essentially, before it gets to minus 132, perhaps a day and a half. Depends how big the leak is, of course, but under normal conditions, this is how long it takes if you artificially fail a vessel by drilling a hole in it to release the vacuum. If you wait for the sensor to be full into vapor, you've now lost 22 hours of your grace period. So you are much better looking at liquid sensors than just temperature sensors. We always use both. Now, transferring between one tank and another, if you use consistent inventory units across tanks, and ideally have all the same model of tank, then it's very, very easy to move specimens from one tank to another, and it takes a very few minutes. Well, depending on the size of the tank, but a 10 canister tank can be done in 5 minutes. So to do this, you would work with a colleague, obviously for safety in a cryobank, and also act as your witness. And I would strongly recommend video recording the entire procedure to prove what you did. You move the failing tank next to the backup tank. Why? Not the other way around, because the backup tank, all tanks for storage should be moved as little as possible. So let's leave the good tank where it is and move the one that is failing already. Then transfer each canister or goblet carrier, so we have a standard canister or even these sorts of things, one by one, rapidly and directly from their position in the failing tank into the same position in the backup tank. And since all these visotubes remain full of liquid nitrogen, the specimens stay stored in liquid all the way through, and from one tank to the other will take 5 seconds perhaps. You then, once you've got all the things in the backup tank, top it up and then reconnect your monitors and alarms, and it's done, except for the paperwork. You don't have to update your records to show that all of the relocated specimens have got a new tank location. But if your tank was a different size or whatever, they may have gone from one big tank into 2 small tanks. You've got to have 2 tank numbers, and you're going to have to change all the locations within the tank as well. So this is why I'm saying it's much easier if you just go from tank E to tank J, and it's very simple updating of records. So take-home messages from me. I consider CBS high security devices to be the safest form of packaging for cryopreserving human gametes and embryos because they achieve effective biocontainment in enclosed specimens. Whether you believe in the need for this or not, it doesn't matter if the regulators believe in it. If the regulators think there's a risk, it doesn't matter what you believe, you are required by the regulators to do what they tell you to do. We've got many options for device color and identification and labeling, as well as the wide permutations of goblet and visotube shape, size, color combinations. This makes it very easy to create numerous unique storage locations within a cryotank that are easy to locate even through that liquid nitrogen vapor fog. And I'm saying it again, visotubes remain full of liquid nitrogen during handling, enabling safe access to and safe movement of specimens. If you find somebody punching holes in visotubes, tell them to stop. They're giving away one of the greatest features of this form of inventory system for cryobanking. So that's the end of the main webinar, but I have a few quick slides on additional background on the CBS devices. And this information, because it's not widely known and it's not easily available necessarily, I'm going to show the slides each for a few seconds. You could go back and look at them in the video recording. I'm not going to cover the slides. You can go back and look in the video recording for this information. And of course, you can contact Cryo Bio System for the details as well. But there's a lot of information on these devices. They're introduced in non-ART markets 3 decades ago, just over 3 decades ago now. And they're used for many, many things. ART cryobanking may be what we focus on, but it's a tiny, tiny part of the whole cryobanking industry. And one point down here, these sorts of high-security devices are used to store pathogens, even P4 pathogens such as Ebola. So if they're safe enough to store Ebola without it risking escaping, we know they're virus-proof. They came to the ART markets in 1998, and obviously Seacos started to use them, Cryo started using them, and wildlife breeding resource people use them because they're great for biodiversity and genome resource banking. There are many technical features of these which usually make people go to sleep, but the important things are that these things are specially designed not to contaminate the outside of the device when you're filling them, unlike the old type straws we dip the end of the straw into the semen crab protected mixture. So we know that besides them being bacteria and virus proof, the way they fill prevents the outside from being contaminated and introducing contamination into the tanks. They have been tested and validated with both bacteria and viruses and bacteria do not get into them from the outside and do not escape from them if they're put inside them to start with. There's data available, but we know that they achieve this. So thank you for your attention, and I'm now ready to take any questions and answers. Jean?
Thank you very much, David. That was quite informative. That was a lot of information, and nitrogen tank storage optimization is finally a real science, right? So we have our first questions coming from Switzerland. I have noted it. Okay, what is the best ratio between the tank capacity and number of tanks for the best risk management? Everything in a super large tank is at more risk than storage spread over several tanks.
That's like any risk analysis is going to be very much up to your own perceptions. If you're working with those small tanks, yes, you have got literally less eggs in one basket, but those tanks require you to fill them up. They have a certain static holding time, but they are each tank should not be moved, because every time you move a tank, you risk damaging the weld or the glue around the neck. So you shouldn't be moving those tanks, which means you need a lot of floor space, which means it's you've got to have some way of getting liquid nitrogen to all those tanks and topping them up, and you've got to measure the levels and top them, because if you're relying on these things for those tanks to monitor them, we would actually we'd fill them once a week and measure the level of nitrogen before we refilled it and plot that on a control chart and know if the tank is behaving normally. I have had 3 tanks fail in my career, actually on 3 different continents, or at least they started to fail. But we have never lost a specimen. The first time was by sheer good luck, because this was back in the 1980s. We were still learning a lot of things in those days, but my staff commented the tank was losing more nitrogen than the others, and so we transferred specimens straight away. Then we started doing the monitoring stuff. So that's the one side. The other side is the big tanks. Yes, they hold more in one basket, but they work on autofill. So they are automatically filled with liquid nitrogen. They are maintained full. The system lets you go down to a certain level and fills it up. And it will, as long as you have a supply of liquid nitrogen, it will stay full. Even if the tank is starting to fail, it is trying to fill it all the time. So it will still keep things cold, and it will be ringing alarms because it's using too much more nitrogen than expected to use, and therefore you will know and be able to transfer. So it's a balance, and there is no absolute formula. It's a balance that each person or each cryobank would take. If you think about those cord blood banks, they are using those very high capacity tanks. They've obviously done their risk analysis, and it works. I don't think that cord blood is perhaps quite as valuable as some of these embryos, but do the risk, work it out. But the thing is, you need to be managing your tanks properly in terms of monitoring, alarms, filling practices, handling practices, and then you decide. If you want to have a room with 50 or 60 35-liter tanks in it, that's your choice. It's just going to take you a lot more space and your staff a lot more time to monitor them and keep them topped up.
Thank you, David. I have another questions here. What is your opinion? Oh, sorry, I lost it. I'm sorry. I chose to try it again. Okay. What is your opinion for vapor phase cryo storage?
Personally, I would never use it. I can see the attraction for people who are worried about cross-contamination, particularly with storing in cryotubes. There was a study quite a number of years ago that showed that probably 30% of cryotubes leak. And what happens is that even though you think you tighten them up, when you get the shrinkage as it freezes, the seal becomes less than perfect. So because there's usually about half a mil of air inside the cryotube, when that air gets to minus 196, it has a much, much smaller volume. So it creates a significant partial vacuum inside the cryotube, and that sucks the liquid nitrogen into the cryotube. So that's where the contamination comes from. Now, whether you believe in cross-contamination or not, as I said, if the regulators do, it's still your problem. So for me, I think the dangers in vapor are not worth what might be a possible saving. You have got much less time because you only have a small amount of liquid at the bottom of the tank. If that fails, you've got a very short period of time before the whole tank goes above minus 132. So for me, I would never use it. I prefer to be in liquid and have all that extra grace period if a tank were to fail. And I know that the handling is much easier because, as I say, if it warms up above minus 132 and you put it back in the minus 160 vapor, it does not get back below minus 132 in as quick a time as it goes back into liquid. It's 1,500 times faster heat transfer with liquid than with cold vapor.
Okay, thank you very much. Another question, is there a really need to clean tanks on a regular basis to avoid bacterial contamination of the liquid nitrogen?
Not if you're using high security devices, but it doesn't matter. I've often said to people jokingly that you could actually store them in liquid manure if you wanted, and it wouldn't affect the contents because of the proper handling of the devices. But seriously, for me, if you don't use high security devices, then you should do a risk analysis of what you're going to be cleaning out of your tanks. Now, that white sludge that accumulates at the bottom of the tanks, remember, that's just very fine ice particles. That is actually that fog that forms the top as it settles, which is just fine ice particles. It will sink to the bottom of the tank and accumulate. So that's what's in there. When you open a tank and you've got the fog, do not blow into the tank to try and get the fog out of the way. That's the last thing you should do, because all you're doing then is freezing all your exhaled air with all of your oral and lung bacteria and COVID, if you've got COVID. All those things will be put into that fog at the top and would then sink into the tank, so you'd contaminate it. If you want to get rid of the fog, use a very like a small vacuum cleaner on low suction pressure and actually suck it out. But if you just wait, it settles anyway. But the point is, what's at the bottom is ice with local bacteria in it. If your specimens are in that ice, then it's a problem perhaps, but that ice is always floating down through the liquid, so it's always going to be in there. So yes, people should clean tanks occasionally if you're using things like cryotubes. We have not faced that situation except for the occasional donor sperm tank for many years, because we use the high security devices for preference, and it doesn't matter because they are independent storage. They will not be contaminated by whatever's in your tank.
Thank you, David. Another question from Austria. Thanks for the presentation. We have never heard of a tank failing. What's your experience? And do you recommend to replace tanks after a certain time, David?
Okay. Well, all I say is you've been lucky or fortunate, so that's fine. I say over the years, we've had 3 tanks that have shown signs of failing, picked up by virtue of the fact they're using more liquid nitrogen. Week by week by week, they use more, take more to fill up each week. Obviously, if you had to go searching for a straw that you drop to the bottom of the tank or something, that week you will have a lower nitrogen level. You come back to top up. But if you're topping your tanks up 2 or 3 times a week, you will never know if a tank's starting to fail. unless you're monitoring the tank. So if you're filling them up every 2 or 3 days, as I've seen some people doing, and you're not measuring levels, then you will not know if your tank is starting to fail, and you'll just keep going until it becomes more catastrophic. So 3 times we've had this problem where tanks have been using more nitrogen, and we've just moved the samples to a new tank and got rid of the old tank. How long should you replace them? Well, depends on your risk analysis. If the manufacturers put a 10-year life on a tank and you use it beyond that, then you are taking perhaps more of the risk, but the manufacturers don't accept any risk anyway, so it doesn't make any difference. If you buy tanks regularly, you will know that new tanks can fail perhaps more often than old tanks, because old tanks that you've had for a long time may well be better built than some of the newer ones. They may have been welded in the neck rather than glued in the neck to join the inner and outer tanks together. So you have to see the maybe regulations that you are allowed to use things beyond warranty period, for example. Depends on local regulations. Personally, I would not throw out a tank just because it happens to be 10 years old. If it's worked perfectly for 10 years, then it has just the same likelihood as continue to work for 10 years, whatever. But if it does start to fail, we will know. We will know quickly because of the way we monitor the tanks with measuring levels and plotting them, but also the temperature sensor and the level sensor. So it's a risk analysis within your regulatory environment.
Okay, David, thank you very much. We have a question here from South Africa. How many years does the older, smaller tank last? Okay, and what to do if the vacuum of the tank breaks? Okay, will you use all your samples?
Okay, we've had how long do they last? The answer for that is a piece of string. They will last until they fail or until you throw them out. And when either of those things happens is not predetermined unless you're throwing them out based on warranty period. So if we do have a tank start to fail, we will know before specimens are compromised, because we will know based on the level of nitrogen usage. The specimen will not have been compromised. We would simply transfer them into another tank and continue with storage. As I said, we've had 3 tanks show evidence of failing. We've never lost a specimen.
Okay.
So I hope that answers the question. If they want a supplementary, please ask a supplementary.
Okay, we have a question here from Philippines. Okay, what if oxygen sensor that you recommend for LN2 leak?
Every cryobank is a risky workplace. It's a dangerous workplace. So we would design cryobanks because the liquid nitrogen is continuously evaporating, will accumulate at floor level, but nitrogen is lighter than air, but cold nitrogen vapor is heavier than air. So under normal conditions, it will just accumulate slowly. So we would normally design a cryobank with a extraction from low level at the end of the room, furthest from the door. And we put a transfer grill at the bottom of the door. So like a little grill will allow air to come into the room, and at the far end of the room, we'd be sucking out air at a very low rate from the floor. And you may only come on from time to time, it's up to you. But the oxygen depletion sensor should be no more than like a meter off the floor. If you put it higher, then that means you've got more risk. So put it at a meter off the floor, 40 inches, and that means that even if the nitrogen accumulates to that level, people won't be dying from suffocation because they're taller than that. If you've got very short staff, then you might want to put it lower, but do not put it at 5 or 6 feet. I've seen cryobanks with oxygen sensor at 6 foot or even higher, 2 meters in one case. And I have a nice photograph somewhere of a 5'6" lab director leaning against the wall next to an oxygen sensor that's about a foot above her head. So oxygen sensor, when that goes off, you've got audible and visual alarms inside the room and outside the room with signs saying, if you're in the room, get out. If you're outside the room, do not go in. And at that point, we would also tie that alarm into a management system so that the extraction system would go into turbo mode and suck a lot more air out of the room from ground level, so sucking that nitrogen vapor out from ground level. You may need to have a separate fresh air supply at the other side of the room from the extraction vent to help it flush, because otherwise you'll just be able to suck a lot of air through that small grill at the bottom of the door. And that would be that fresh air we put up at ceiling level, so it would be sucking in from the top at one side and flushing through and out at the bottom of the other. So that's how we designed cryobanks for many years. That makes them safe places, but there's still a possible risk. The biggest time you'll like to see those alarms go off is when you're refilling lots of small tanks, because you're playing with a lot of nitrogen and that will accumulate. If you have no ventilation, it will accumulate and keep ringing the alarms, which is very annoying because you must leave the room because you are at risk. People have died in cryobanks, bigger ones always, but people have died in cryobanks because of asphyxiation.
Okay, thank you, David. We have another questions here. I think it's coming from Jordan. Okay, which is a better, closed or semi-closed cryopreservation?
Well, the only thing that worries about closed or semi-closed is vitrification. Most cryopreservation is in other devices, and they're all closed, sealed. Personally, we were slow, if you like, in one sense, to take up vitrification because I was not willing to voluntarily vitrify specimens that were exposed. So we did not change from freezing of our embryos in high security straws to vitrifying in HSV devices, let's say, until 2013. So at that point, there was evidence that they were as effective as other devices for both embryos and for oocytes, so we made the change. My preference, if I have the absolute choice, I would say I would always use the devices that are validated to achieve effective biocontainment. That means if somebody else goes through the validation process, their products would meet that criterion. If you don't want to use those devices, you want to use something else, then I would still use a more closed system like the Cryotech one, for example. But I would say, for me, closed and ideally biocontained. And the latter would be my personal preference.
Okay, thanks, David. We have a questions here from Estonia.
We're getting around the world, aren't we?
Yeah, we are traveling. That's good. Yeah, a question from Estonia, but it's because it says probably silly questions. Okay, there is absolutely no silly questions. So
only the ones you don't ask.
Do you keep goblets with lid on in LN2 tank? How you mark closed goblet outside?
Okay. So that's two questions. The first one, do we use the lids on or off? Now those, yes, I'm sorry, Jean, those lids are a pain in the posterior. They're always hard to get on and off. That's why we like to use those carrier type systems, because they have the base for the layer above is like a shelf, and it acts as a lid for the layer below. So you don't need the lids on the goblets, which is a major thing. That's the biggest pain that people have is working with those lids. So we like those carrier systems, and you can even get those carrier systems that will fit into ordinary canisters or replace ordinary canisters if you wish. So you aren't stuck with using goblets in canisters even. But you use those, and the lids become a thing of the past. So that was the lids. But what was the second part, Jean?
Oh, sorry, I didn't get it.
What was the second part of the question?
Yeah, hold on just a second. I'm just trying to find it again.
It was the lids. The lids.
Well, I'm sorry, I cannot find it. Sorry about it.
Yeah, what was it?
Okay, I have another questions here.
Sorry for the question. I'll send it again.
Yeah, definitely. Yeah, we have a questions here from Ivory Coast in Africa.
Wow.
Okay, it's written in French, but I will translate it in English. Okay, how long can we preserve biological sample in LN2? Okay, and does it exist a maximum duration of conservation?
Okay, so if you want to go back to the very beginning of cryobiology for embryos, for example, it was David Whittingham, Peter Mazer, and Stanley Lebo made that achievement. They did some calculations. I think it was David who did the calculations, but it may not have been. Unfortunately, Stanley and Peter are no longer with us. But they did the calculation, which was based on the risk of damage to the DNA in the embryo cells from cosmic radiation hitting the planet and getting into the tank. And their estimate was 1,000 years. Obviously, no one's tested that yet. So I would think that for all intents and purposes, the storage is at least 1,000 years. If you created a lead-lined room, perhaps it would be even longer. The answer is we simply do not know, but it's very long. The reason why some specimens show poorer quality, and this is often seen in the bovine sperm industry, for example, with longer storage, because of poor handling. The straws have been taken out, put back, taken out, put back, and they've accumulated cryo damage, or for poor shipping or poor handling during shipping. That the shipping tank arrived and was left too long, or the transfer from the shipping tank into the local storage tank, they just took too long. They were reading, checking the labels and putting it in, check the label, put it in. Those things take too long. So that's where this idea that longer storage is poor. It comes from poor practices rather than the poor storage in liquid nitrogen. So the answer is longer than we really care to think about.
Okay. Another questions coming from India, I guess. What is the more effective way of Umbrio cryo device storage in the LM2 canister?
For me, the ones I showed. That's the ones we've worked out to give us the most locations. And so it's the most storage locations, and you can scale things because there's a huge variation. There's many permutations that you can create for yourself using the different types of shapes and sizes of visotubes to configure for your practice. If you're typically storing 5 embryos per patient, you would probably use a slightly different system, the hexagonal one, because you only get 3 HSV devices per location. But if your alternative gives you 8, that's nice, but it might be cheaper than or more efficient to use 2 of the smaller locations. You have to work that out for your local circumstances. But for me, this is the most efficient in terms of achieving capacity in the tank, but also efficient in terms of how you can handle them, how fast you can find a specimen in the cryotank. Because looking by shape and color, right down to the actual specimen's location, gets you to the specimen the quickest and easiest possible. And then you only have the final check of the label rather than to do 2 or 3 layers of checking. It's very fast. Yes, there may be an issue if you happen to have a colorblind member of staff. You might consider something like this as an in-basket test for them, or work out some way of just making sure that people with color blindness do not go looking for specimens in your cryotanks.
Okay, David, guess what? I found the second part of the missing question from Estonia. Okay, good. So how can goblets get marked from outside to find the right one?
Marked as in labeled? I'm assuming it's, let's answer a couple of ways. If it's labeling, we label the goblets before we put them into the tank. So when we're commissioning a tank, we will prepare the goblets. So each goblet will have its tank and its canister or carrier written on it. And if it's an upper or low, we would probably write that on as well. So each goblet would actually be identified. So if you had 2 goblets out in a working box, each goblet would have written on it the tank, the canister or carrier, and its level information. If you're fixed with colors, like I showed, red, yellow, green, blue, you don't need to worry about the layers because you know which layer it goes back in. It goes back in the red layer or the blue layer. So they're labeled and then prepared with the visotubes or whatever according to your combination system. Then that unit is frozen with liquid nitrogen in your cryotank. So this is done before you even put the first specimen into the tank. You've commissioned it, or you might commission a carrier. So another carrier may be empty. So you could actually, when you need it, you can then commission the next carrier and get it all frozen before you start putting specimens in. So you aren't trying to write on anything that's frozen because it doesn't work. If you're worrying about the individual locations, if you're using the small visotubes on canes, you label them before you put them on the cane. But if it's working within this color locations, as I said, if we fix like the hexagonal things, if they fix so they can't come out, a visotube cannot come out of the goblet, then you don't need to label individual visotubes because the visotube is never taken out of the goblet. The goblet is the storage unit, And even if you take the goblet out of the storage tank into your working box, under appropriate working conditions, you have minimal risk because your working box is already full of liquid nitrogen. And you're always working with two people. You're never just working on your own. You should never work on your own in a cryobank anyway. So I think that probably answers the question. If you want to know what's in the cryobank from outside the tank, then there are some RFID-based technologies being developed that will allow you to identify exactly what specimens are in your tank and where they are even. But I think there's a couple of installations that are still developmental. I don't know anything in more details. Of course, there is the Tomorrow type system, which is fully robot automated system. I'm not sure about the space efficiency of that. I know it is more expensive, but they take all the liability as well. So I guess there's that issue as well.
Okay, David, we have another questions.
Mm-hmm.
Coming from the UK, questions and a compliment. Thank you for your super presentation, David. Many of our prospective customers are reluctant to switch from open to closed vitrification system as you did in 2013. Okay, what would you advise to them?
They should have watched Etienne's presentation 2 months ago. But what I mean, so I'm a very skeptical scientist, but I waited for the papers to come, which they did back then, showing that they were as effective. And so with that information, then you can show that they are as effective. So that problem is resolved via the literature. There was another paper quite recently that was comparing high security devices to, I think it was Cryotop, and it was published in the last couple of months. Can't remember exactly where it was, because I go through so many journals every month. But there's another paper published recently. It was from either Spain or Italy. Actually, I think it was Eleonora Porcu was the first author. Yeah, I think Porcu was the first author. So look for that paper. But that's there. So if the question's from somebody in the commercial side, you need to pull together these papers and provide them to the customers as the evidence.
Okay. Another question's coming from Ivory Coast. If there's any software that you can recommend to manage the traceability of the storage inside the LN2 tank?
Traceability inside, I mean, you mean as in just an electronic inventory system, or as in something that keeps track of things automatically? Because if it's the automatic part, then there are some systems under development that will keep track of things automatically for you. But I don't know that they've actually hit prime time yet. In terms of inventory, there's a whole bunch of cryo softwares around that will help you keep your inventory rather than using Excel spreadsheets. The EMR IVF database that we've used for many years, called Ideas from Melwood Medical, has a very effective cryobank system in there that obviously has a full electronic record of where everything is. And even when you come to freeze a specimen, it links you into your electronic cryobank to find a location, so you know where it's going to go. And when you come to thaw a specimen, the system tells you where it's stored. So all information is there in one place. And with backups and stuff, it's completely safe. Some people still, of course, like to keep paper records as well. And that, again, that's up to you. That's up to your risk management. If you think that if you're storing your database off-site, that's very risky if the internet goes down. So you might keep a local version. You might do a dump to PDF of your cryobank module information, so at least it's available to the last dump to PDF. I'm not quite sure exactly what the question is in terms of managing it, as I said, with an EMR or a database compared to Excel, or if it's one of the RFID-based systems. But the RFID ones, there are a couple of them under development I know of. And I'm trying to think what one of them is called Custodian. The other one is CryoGat. They're both coming out of the UK.
Okay. Another question, I guess, coming from Switzerland. Is there a really need to clean tanks on a regular basis in order to avoid bacterial contamination of the liquid nitrogen?
Didn't we get that question already? I'll answer it again. The bacterial contamination comes in from room air, exhaled breath from staff, and so it's going to get in. Do you need to clean it? The answer I gave before, cleaning, it depends on what you're storing. If you're storing high security devices, we do not bother. We don't clean tanks because the icy sludge in the bottom is not going to affect what's stored in the devices. If you're using non-sealed devices, especially open devices, then you have to take your risk management approach because you'd have to move all the specimens to a new tank to do it, and the risk of transferring them from one tank to another is going to be significant depending on how you've structured your inventory system. But if there's a risk of those specimens coming out of liquid nitrogen during transfer from one tank to another, then that's very, very risky with the vitrified specimens. So it's a risk analysis.
Okay. Questions coming from Nigeria. How best can we cryopreserve sperm in order to preserve the viability of fused twitches sperm?
Of what?
Of few twitching sperm.
A few twitching sperm. Okay. Well, since the few twitching sperm will probably be used for ICSI anyway, there's a whole range of approaches. My personal preference is always to freeze semen samples rather than wash sperm, because the protein in the seminal plasma seems to help protect the sperm during the freezing and thawing process. But with a twitching sperm, depends on if you can purify them with a density gradient or something. You have got some very small size vitrification devices nowadays, which would allow you to vitrify. I'm not sure how you can effectively make those biocontained. I'm not sure if the very small one, which comes from, well, I've seen it at Nordic Cell, a company in Denmark, and they have this small device, and I think that device might fit inside, after it's vitrified, might fit inside a high security cryotube. I'm not sure. So it's a difficult question. There's another paper just came out recently about talking about using a cell-free scaffold, which is a nice name for saying you're using a zona pellucida. Some people have actually put small numbers of these sperm, picked them up separately, put them inside a zona pellucida, and then use that as their very sub-packaging unit before they froze the sperm. But twitching sperm do not survive cryopreservation very well. So if you've got the sperm that have been twitching and you manage to cryopreserve them, whether it's slow freezing or vitrification, and they don't show anything post-thaw, if you had purified them before freezing so that it was only twitching sperm, then at least you know that they're only recently dead sperm, so that their amount of autolysis and other damage internally will be very small compared to sperm that have been dead for an unknown period of time before freezing. It's hard to judge without knowing the specimens, I'm afraid.
Okay, another question is coming from Ivory Coast. It's in French, but I will translate it in English. Liquid nitrogen, vapor nitrogen, what is the ideal temperature in terms of cryopreservation of sperm, advantages and risk?
Anything mentions risk, you have to work it out for your own circumstances, but you must keep the specimens below -132. So the risk of them warming is much higher if they're only in vapor or ultra cold air. I've said my preference is I would always store them in liquid, because the liquid storage means that they are -196, give or take a fraction of a degree, and therefore you will have the maximum storage. You'll have the maximum preservation and least risk of recrystallization damage during handling. The risk is much higher if you're working with a vapor or ultra cold air tank compared to always in liquid, in my opinion. So that's how we've been running banks for 40 years. I have seen no reason why I should consider changing. Yeah, if there's a supplementary, please ask.
Okay. We have another question here. how do you suggest we cryopreserve testicular tissues, vials or straws? Okay, how do you load tissue in straws without dipping the straw into the solution? Is this an effective nozzle?
Okay, this does give us a little bit of a vexed question. We would prefer to freeze the macerate. So after you've teased the tubules apart and that sort of thing, we would freeze that material or just the isolated sperm if possible. Getting them into the device, yes, can be tricky. There are ways of doing it. If it's very small things, you could actually put some cryoprotectant, medium cryoprotectant mixture inside a straw, and then pick up the tissue or whatever in a small handling device. So like a larger bore stripper or flexiped, and then use that to put it inside the straw. If you have to do it in a way that involves dunking the end of the straw into the specimen, then you do that, but then you must sanitize the outside of the straw before you freeze it. And sanitizing the outside, CBS will give you their approved list of cleaning agents that are judged safe for cleaning these sorts of devices. But that would be another way around it. But we would typically freeze the macerate or whatever in straws to get the better heat transfer, because the survival will be better. Remember, judging survival is not just a question of whether the sperm are motile or not. It's how fertile they are, how good they are at getting patients pregnant. And it's very hard to measure that because no one's done any direct studies. But I did an analysis a number of years ago. It's in a paper I published in RBM Online, 15, 16 years ago, on cryobanking of sperm, and looking at how many sperm you need to inseminate to get onto the plateau of the fecundity curve. And it seems that if you compare cryotube or cryovial frozen sperm to straw frozen sperm, you need 4, 6, perhaps even 10 times as many sperm to be inseminated to get on the plateau of the fecundity curve compared to sperm stored in straws. And the straw data obviously come from the French Fédération Sécos. So my answer is, it's not just about return of motility, it's about the total functional competence of the sperm. And yes, cryotube stored sperm might look to be just as motile as straw frozen sperm, but I am not convinced, and I have indirect evidence to support the opinion that they are less functional. So that's why we stay in straws.
Mm-hmm. Okay, another question from Vietnam. How long can we store sperm?
As far as we know, the same amount of time as you can store embryos. So 1,000 years. And again, the big issue is how do you handle them while they're in storage? And my example was the bovine sperm industry, where they've had many situations over the years where samples have been mishandled and are just all dead or whatever by the time the farmer thaws them out to use. So a lot longer than you're going to care about is a simple answer, but it could be a very short period of time if you don't handle things correctly. Okay. So balance your techniques against your functionality.
Okay, we have another questions here, also coming from Vietnam. Okay, I am having questions regarding cooling down system. What can I do when cooling down system has a problem during cooling down? Actually, my program is 1 degree per minute until -80 degrees. When sample temperature goes down to -20 degrees, the cooling down system is stopping. So what I have to do with this trouble? My sample has stem cells or umbilical cord cells. Sorry.
I can't tell you exactly for those types of cells because I've never frozen them. But certainly what we have said for sperm and embryos is if you have a problem that's down to the -20 sort of region, your best thing is to warm them up and then reprocess. and then, warm them up and then put them to another freezing system. If it's below -40 even, you could, for sperm, you could just immerse them straight to liquid. Certainly below -80, absolutely you could do that. It depends on the cell type and depends on your cryoprotectant and your cooling curves. So this problem has occurred with some freezing systems, particularly ones that use a solenoid device to control liquid nitrogen flow. If you're in a humid area, then there's a greater risk of getting ice formation on a solenoid valve that will cause it to jam. That was much more a problem in the older days, and I think it's been largely fixed on the more modern machines. But that has been a problem. But you need to think about your cooling curve and decide where it's safe to warm them, to allow them to warm up, and then put them into a new system, or whether you would just put them straight to liquid nitrogen. It's hard to tell. If it's a solenoid problem, there was a guy, I won't say his name, but there was a guy in the States, and he said if it's this particular type of machine, he would basically lift the machine up a couple of inches off the bench and just drop it, and it would perhaps free up the solenoid and it would continue on the cooling curve. So if that's the problem, that's the sort of thing you can try. I can't recommend it, but I know it has worked for people in the past, and we have used it in the past on occasions in the old days for slow freezing of embryos, for example. It depends on the systems and stuff.
Okay, and it just reminds me that the cryopreservation of tissues will be one of our next topic. One of the next topics we are going to have with webinar during 2021. Okay, so it's really a very, very large topic. Okay, and
much bigger than ART.
Yeah,
so
and there is so many things going on in this area, actually, that's for sure.
Yes,
that's for sure. Okay, so it has been 1 hour and 30 minutes. We are online, actually. If there's any other questions, apparently I do not have any further questions here. David, the one I have already asked you, I'm not going to re-ask them again. No, I think that's it. So, David, thank you very much for your time. It has been great to have you online today. A real pleasure and honor for Cryo Bio System. Okay, I'm pretty sure that all the attendees will get back home with tips to apply directly into their laboratory. They all know that if they have further questions for you, they can address them directly either to you or to Cryo Bio System, and we'll transfer them to you. Okay. Thank you very much to all of you. It has been a pleasure, and we really hope to see you on our third webinar, for which you will receive very soon some notification. Thank you so much. Bye and stay safe.
Thank you. Bye-bye.